So, hello everyone. Welcome to this conference about graphic testing. So, here in this case, I want to present you a little bit on how to test graphic testing, but when you don't have any hardware. So, I will show you how to use VKMS. So, first, what we want to test, then what is VKMS, and all the possible options you can find in VKMS, and most importantly, what are the current work of upstreaming around VKMS. So first, a little bit about me and my company. So I am an embedded Linux at Bootlin. We have a strong embedded Linux expertise and also a little bit on the Zephyr side. We do some development, consulting, and training stuff. And most of our work is open source, so you can find us in I think most of the Linux releases, a little bit on the Zephyr release, and a lot of other open source projects. And me specifically, I am the current VKMS maintainer since a bit less than one year. So I will start to present what is display testing. So first, what we want to test is, in this specific case, any device that can have a screen, and one of the important parts is an application where you don't know exactly on which hardware it will run on. If you know exactly which hardware you have, you don't need to emulate anything, you don't need to buy a lot of boards, so VKMS is not really useful. It can be used, but not really useful. So how we can do it? If we take the path without any emulation, you will have to buy some boards to set up the boards, to debug stuff, and go back on step one because a user decided to use another laptop, another computer, and another graphic card, and so on. So it can become expensive and very annoying to do with a lot of physical manipulation. With VKMS, what you can do is just start a virtual machine, set some VKMS configuration, and debug what is the problem. So those two solutions are complementary because when you need to test some hardware features, most of the graphic controller have specific sometimes specific issues, sometimes specific quirks, sometimes very specific hardware blocks that is not possible to emulate with VKMS. So you may need to have some hardware in the loop, but this is obviously a little bit expensive if you want to do it at scale. And for example, if you are GNOME or Mutter or GNOME or Kadir or I don't know, any other stuff, you will need to buy thousands of computers and graphic cards to check your software, and you don't want to do it. It can be also a little bit difficult to integrate in CI. It is a big work that is done, for example, in kernel CI or DRM CI. They have a bunch of different hardware, and people are working 100% on it to make it work. On VKMS, on the other side, it's it's free. You don't have to buy anything to make it run, and easy to automate because it's just a virtual machine and some script inside the virtual machine. But yes, you don't test the hardware itself. So if you have a broken hardware that behaves very strangely on a very specific configuration, you will not be able to test it with VKMS. So I think I did not present VKMS yet. So first, what is VKMS? VKMS is virtual kernel mode settings. So this is a little extract from the documentation. It's a fully software graphical display controller. That means you don't need any hardware to use it. For example, I spoke about virtual machine. But you can also run it directly on your laptop, and That's all. That's really just a software stuff. So V is for virtual, and the KMS is just a way to say that it uses the standard Linux graphic API. So if you are already having an application that uses DRM and the KMS API to display stuff on the screen, to use VKMS, you don't have to change anything. It should work out of the box, hopefully. So yes, the main goal of VKMS is really testing the user space. By user space, I mainly think about compositor, for example, or graphical libraries like Qt or, I don't know, maybe SDL or GTK can directly output to DRM buffers without any compositors. So yes, it's really this kind of application. If your application is more high level, like, I don't know, a web browser of stuff like that, maybe it's a bit overkill. So I will do a quick overlook of the display pipeline because that's what VKMS will do, emulate a full display pipeline. So yes, you can see the cursor. You are the user application and you want to test. You are a user application and you want to display stuff on the screen. What you have to do is to configure all those blocks. They are hardware blocks. So technically, here you can see in red, green, blue the pictures you want to send to the display. So you will send it to some planes, or basically just frame buffers, and the hardware will take these planes to feed the CRTC. CRTC is the hardware block that will grab a full buffer and generate a stream of pixels. Then this stream of pixels is fed in the encoder, and with the role of the encoder is to take the stream, which is a numerical internal to the SOC, and generate the proper electrical signal to, for example, a connector or a panel or whatever you have on the other side. And the connector obviously is a representation in the kernel to also attach some other stuff, like maybe audio if you want to use HDMI, or if you use USB-C, it will also attach to the USB-C parts and so on. And you will have the display. So in this case, VKMS will emulate everything from the plane to the connector. That's really convenient because when you want to display something, the user space needs not only to send the data, but configure properly the plane, configure properly the CRTC, the encoder, and the connector, so the pixels properly go to your display. And that can be a little bit difficult. What VKMS is able to do right now. So as I say in the introduction, I will present current working upstream, current stuff that is working in the Linux upstream, current stuff that it is working on the mailing list, and planned stuff that I have ready, but I don't have I did not send the series yet because we need a bunch of stuff before. So current upstream capabilities are plane composition. If you take a look at a lot of graphic display controller, you will see that they can grab multiple planes to compose one output. So in this case, you can see I can configure it to take 4 different planes and generate one output. This is useful, for example, for the cursor here. It is nice because your cursor is most of the time the same. You don't have to send the picture again and again, and you just have to change its position on the screen. So it's very convenient just to say to the display controller, please put this plane at this position. Overlays can be used, for example, with hardware offloading of composition, and most notably if you do some video capture or video decoding. So basically for video decoding, you can just ask the decoder, please put all the video in this buffer, and then ask your display controller, please display this buffer. That means that you don't have to do any copy in RAM and any treatment from the software from your application, and you don't have to manage anything, and it will reduce the power consumption. So what VKMS can do also is some color conversion stuff, because obviously we are working with images, and images have a lot of ways to represent colors. So here, for example, we have R24, which is the standard RGB 888, so 8-bit per component. But sometimes, for example, the cursor can only do a smaller set of a subset of this color encoding. So here it's only RG16, so RGB 565. Or, for example, if you do some video decoding, sometimes you have YUV video outputs. So instead of decoding it in YUV, asking to convert it in RGB and send it to the display in RGB, you just ask the display controller, I give you this YUV buffer, and please put it on the screen. So in the case of VKMS, we do all this conversion, and that allows you to really emulate what you can do with physical hardware. So here, that's the last and probably one of the important part for testing is, if you remember the previous pipeline here, your application never see what is on the display. It's data, and hopefully it is on the screen. In DRM, they have a very nice kind of connector, which is a write-back connector that allows a user space application to grab the output buffer generated after all the composition and everything. So in the case of VKMS, everything is in software, but for example, I think AMD GPU and Intel GPU, and probably NVIDIA one, I don't have one, can do the same thing. You can ask to the display controller, please give me back what you will display on the screen. So in case of testing, it's very nice because you can send a picture and check that it is exactly what you wanted to display. So what you can configure now, because all of this is, you can have a lot of different pipelines. So currently we only have 3 different kernel arguments to configure it: enable cursor, enable write-back, and enable overlay. What it means is that if everything is false, the minimal configuration you can have, you can see using VKMS, is one plane, one TC, one encoder, and one connector. This is nice because it's already, from the user space point of view, it's already a graphical output. You can already use it to display stuff. But it's not very representative of what modern hardware do. So they added a lot of configuration. If here, this is the maximal one we can do. So we can see that we have one primary plane, the same as before, but also 8 overlays and 1 cursor. And we also have this nice write-back connector. So it's already in a big step to be able to configure all of this, because you can check that your compositor, for example, work properly if you have only a primary plane, or if you have only a primary and a cursor, or whatever configuration you want. But it's limited. You can only have 8 overlays. You can only have 1 CRTC, 1 encoder, 2 encoders, and 2 connectors, which is not very, you cannot do a lot of things. And to show this, I will just show you 2 real-life examples, a very small one, Texas Instruments SOC, and a bigger one like this laptop. So here is the complete pipeline of the AIM62 switch-through of TI. You can see we only have two different planes on the left side, and 1 CRTC, 1 encoder, 1 connector. So that means that if we want to emulate exactly this today in VKMS, it's not possible. You can either have just one primary or one primary and 8 planes, and 8 overlays, sorry. So yes, we need a little bit more of flexibility on this side. And completely the opposite, this laptop have here, for one CRTC, you can see we have 6 planes, but obviously it's very simple. It's not so simple because I have technically one screen here and possible 4 outputs. So they just duplicate this 4 times. So technically I have something like 24 planes and 4 CRTCs. And on the other side, I have for each CRTC at least one connector, and all the MST connector stuff is when you try to plug a dock on USB-C or DisplayPort, for example, you may see multiple outputs. So here, in this case, we can have up to 5 MST outputs, and they duplicated again this 4 times. So in total, you have an explosion of combination possible, an explosion of possible combinations. So yes, we really need to have a way to represent it in VKMS and to configure it. So that's why we try to introduce a config.fs interface. So config.fs interface needed a lot of internal modification inside VKMS to be able to create, for example, multiple CRTC or encoders or all the stuff to make them dynamic. But this is done, and now we are focusing on the config.fs interface itself. So the work was initially done on the mailing list. I forgot to take the name before here. I think at least 3 years ago. I took over more than 1 year ago, and Jose helped me to wrap up the first set of configurations. And I will show you the current patch that you can find on the mailing list. And I thought you cannot click the link, so this is a link. The name of the series is, I don't remember exactly, not fun, yes. I will take a look after. And you can find a nice branch where I just applied and rebased the patches to DRM MISC nests this weekend. So if you want to test it, just clone it and it should work. We use a new, and yes, I need to show you this in real time. So yes, demo. And it's slow, so we need to introduce a new argument because we need to keep backward compatibility, but we also want to delete the default device because currently the driver, when you probe it, creates a display controller, but we don't want it. So this is this create default dev. So, and it's not this one, sorry. So I will do the probing just after, and we show you what is the difference. So while we are waiting, this will be the main folder where you will configure VKMS. So this is a config.fs directory, and if you want to create multiple devices, you just have to create multiple folders in this, which will be very useful. For example, if you want to emulate someone that has multiple GPU on his computer. That can be the case today. So yes, here. Please. So first, I can probe it. So I don't want to do this. I want to probe it with the default device. Here we can see that when I probe the driver, we created the DRM device. And if I do the same thing with this argument, we don't have any default device. That means if I try to do, please, not this one, mod test, sorry. And take a look, we don't have any graphical output, and that's exactly what we need to do. So here I will just show you how to create a device. So create a device, just create the folder. This is easy, but we don't have anything yet, because when you use DRAM in kernel, you cannot do everything dynamically. You need to configure everything and then expose to the user space. And basically, what we have in this folder is a small file here enabled when where you can write 1 to create the device when you finish to configure everything. So what I mean by configuring is creating all the connectors you want, the CRTC you want, encoders, and planes. So here I will create, for example, a connector. So let's start by creating a connector con1 here. And, create a folder. So basically, everything is creating a folder. To create stuff, just create a folder. And now we have here a connector and some files. So here we have 2 different files. If you remember, each block were connected to some other blocks, and that will be the possible, here, in this case, possible encoders. We will have to put some symlink to an encoders, and it will automatically create the internal wiring in DRAM, so you will see them as connected. And the file status here is the current connection status of the connector. That means at runtime, you will be able to change this one to make the connector connected, disconnected, or in unknown state. So I will next create a CRTC because we add at least 1. So let's create CRTC1 and take a look. Inside we only have the write-back stuff, as a write-back file. So write-back can be enabled or disabled. This will create the user interface to communicate with the write-back connector. If you don't enable it, the only way to grab, you will not have any way to grab picture from VKMS. And it is only 1 per CRTC, because a CRTC can only generate 1 picture, one stream of picture. So you just have 1 per CRTC. Let's do the same thing for encoders. And I want enc1. Here, I don't think, yes, we don't have a lot of things, just a possible CRTC to connect the encoder to some CRTC if you want. And planes. Here is the plane, and the minimal stuff you will have to do is connecting to CRTC again, and also changing the type of the plane, because we have at least 3 different types of planes: overlays, primary, and cursor. A graphic pipeline requires at least 1 primary plane, so we will need to change this. So primary plane is 1. Here in VKMS, in config.fs interface of VKMS, all the values here, it's 1. All the values are exactly the same as the existing one is user space API. So in this case, primary plane is 1, overlay is 0, and cursor is 2. So my dev planes and PLA 1. Not, yes. Sorry. And I think we finished to configure the drive. No, we forgot to connect everything. And for that, I will just take my script and copy 3 symlinks. So here, basically, what I did was just to create all the symlinks from, for example, if we take the connector, connector is connected to an encoder, and I just created a symlink from the possible encoder folder to the connector I want to connect, to the encoder I want to connect to. And same thing for possible CRTC in encoders. I just created a symlink to the CRTC1 in VKMS, and for plane, again, same thing. I created a symlink to CRTC1 in the possible CRTC folder. So now, if I can, I will try to enable the device, and if I did not forget anything, it should work. Echo, yes. And yes, we have a device. So this device is limited. It's a very small one. Let me show you here. So it's called a lot. Just go back on the top. Can I reduce a little bit? Like, is it okay? This? Yeah. So here we have, if you remember, I created one encoder, and yes, we have one encoder. And this one encoder is connected to the first CRTC. That's exactly what we want, because we only have one CRTC. Here we also created the connector, and the connector, I think, yes, here the list of encoders is here, and we see that the encoder is 39, which is exactly what we have just above. All the modes supported by the connector. Here, and our CRTC with not a lot of properties. And one of the important thing is the plane, where yes, we have a plane with only the first CRTC possible and a lot of supported formats. And here, for example, I told you about the values in config.fs. Here we can find again the overlay 0, primary 1, cursor 2. And this one, you will need to trust me, but if I do 30, this mod test is creating a nice pattern on the VKMS output. So yes, you see it's a very nice pattern. Completely virtual. I don't have any. It's a virtual machine. I don't have any specific hardware, and obviously I can't see anything. I will just show you the disconnection status. So if I do this, please. Here, I forgot. What is this? A very strange wrapping here. So the connector is currently connected, which is exactly what we want. But if I want to disconnect it, I just can. So disconnect is 2. Yes. What is this? No more. So I wanted to just echo 1 to sys kernel config VKMS mydev to the connector status here, and if I do again the mod test to see if it's connected, and it's connected because the status is disconnected status is obviously 2. Yes, this time it's disconnected. And if I try to display something on it using again the mod tests pattern generator, it just says me, yes, I don't have any, I don't have anything on the connector. So yes, we just tested that mod test is doing strange stuff if you try to display something on a connector which is not connected. Here, continue to display stuff, but I don't know why, where, because it is not able to create buffers. So this is the current state of the last iteration of the series that we send on the mailing list. as you can see, it's already very nice because we are able to generate a bunch of different stuff, like configuring exactly how many planes we want, how many CRTC, how many everything we want. But it's a little bit limited because, for example, for the planes, we cannot choose the format, the available formats. So we cannot emulate that the cursor only take a black and white color because you have a very strange hardware, or you cannot emulate that the connector should appear as a DisplayPort, and so on. So I continue to work on this in parallel of the upstreaming. So here are all the slides. All the demonstration is here. So I continue to work, and it's not the right slide. Okay. So I did more configuration about everything. So first, more color formats for plain and rollbacks. So that's what's nice to have to emulate more stuff. And for plain and rollback, it's nice to introduce also 10-bit formats and 12-bit formats to do HDR emulation, which was requested by compositors so they can test. But I also introduced a lot of configuration for plain connectors and encoders. So here I don't have anything on the mailing list yet because everything depends on the previous series, but you can find all of the work in this branch. Again, it was rebased like yesterday, so it should work. So here, it's just for readers of the slides. So you have all the commands I will type. So let's go to not this one, but this one. So just a quick look on this. We will probe the driver, obviously. We will create a device with two different planes, plane 1 and plane 2, with one CRTC, one encoder, and two connectors. So, yes, and we will connect everything together, and the plane 1 will be the primary plane. Please. The plane 1 will be primary plane, and the second one will be an overlay. So let's go here, here. Sorry. So I just probe the VKMS driver, and I will take my small script to copy everything until there, here. And here we are. We have all the configuration. So we can take a look direct. No, I don't want only planes. I want everything. We can take a look at everything that is available here. So let's start by not connectors. I will do it at the end. So CRTC, nothing changed. We only have the write back here. For encoders, now you can set the type. So previously, I don't know if you remember, the mod test output, the encoder was virtual, but you can have, I think, VKMS encoders or LVDS or whatever, and this will change the type that will be seen by the user space. Again, the values are the same that are used by the standard DRM user API. On the plane side, we have a bunch more files now. So previously, we had only possible CRTC and type, but now we have stuff about color, format, and rotation. So rotation is basically just if this plane is able to be rotated before being composed on the other planes. So a lot of hardware are able to take the plane, just rotate it before pasting it, and with this you can limit the number of rotation. So we can, for example, completely disable the rotation because you want to emulate hardware which is not able to do it, or you want to enable everything because you want to have them. color encoding and color range are two properties that are advertised to the user space when you want to use YUV. YUV colors need some conversion metrics and so conversion metrics between YUV and RGB, and this basically will control which will be used, and specifically in this case, which will be advertised to the user space. I will focus a little bit on formats because as you can see, I forgot to enable the device, and it's again broken. Yes, enabled. Okay, so if I do this, it will, I forgot this because mod test is a bit strange with VKMS. Here we can see that we have a lot of supported formats, more than before, but your hardware will probably not support all of this. For example, the AR formats, which are just black and white one, will be probably not supported. The YUV 16-bit format, probably not. Sometimes you only have the 24-bit variants of colors, not the 48, which are 16-bit per component, and so on. So we want to reduce the number of available formats in this list, so you can emulate, again, many types of hardware. So I just disabled the device, and it doesn't exist anymore. And now I will just take the commands so you can read them, because previously everything is broken. So this will, the minus star will just disable all the format from the planes. So it will become unusable, not very useful. But in this case, I want to support, for example, only the RG24 format for my primary plane. So I just have to enable with plus RG24. The RG24 and all the stuff you can write here are the DRAM 4cc values. So here RG24, but if you, I cleaned the screen. If you take a look before, it was, for example, RG48 or AG48 or whatever. So here, if I enable my device, where is here? I want to enable it. Completely broken. And I want to display all the formats. So this is the second plane, and the first plane is here. Where is the format list? Just here. Yes, it is way shorter. So my primary plane, the first one I created, can only support RG24. So now you can emulate a very small graphic pipeline that's only do RG24 for this display. So that's a nice thing to have. And what are, oh yes, and now I want to show you stuff about the connectors, and more specifically dynamic connectors, because this is something you can have on laptops and computers and everything that use, for example, DisplayPort, because on DisplayPort you can use one physical connector to plug multiple screens. And what happened in DRM is that when you plug a hub, you will see some new connectors appearing. Like if you have a dock at home, you plug you plug it, and magically you have two more DisplayPort outputs. And that's dynamic connectors. So that means they don't exist in DRM before using them. So that's the goal of the last of the two connectors I created. So just let me take my script again. Where are these? So if we take a look at connectors, here we have, again, more properties, new property type to set the connector type, so HDMI, DisplayPort, or whatever you want. Supported color space is used for HDR emulation. So if you use, I think, HDMI and DisplayPort, you will be able to emulate some HDR properties. So you need to set supported color space. And I also added the configuration of the EDID reported on this connector. So by default, VKMS use a big list of modes provided by the kernel, but with EDID you can just say this is I don't know, Dell screens which can do 4K, or this is a very small screen on the laptop that can do only one specific format, not format, one specific mode, so frame size and frame rate. And what I want to focus on is dynamic and enabled. So a dynamic connector is a connector that you can create and delete at runtime. So to enable it, just I need to guess. I guess it's this. Yes. So you need to write not cut. No. Oh yes, I forgot. Not this one. I need to disable it. This is this one. Not. Sorry. Enabled. I want to echo 0. Yes. So here, if we take a look, completely broken. Same thing. Here. I am out of time. Yes. So very quickly, here if I do echo 1 in dynamic and I re-enable my device, where is my device here? Here, mod test dash here I have two connectors, and if I do here I can disable the dynamic connector, and if I take a look at mod test, it doesn't work because what did I echo? Please. And it's broken. No, yes, it was wrong. So here, if I disconnect, I disable the connector, you can see that the connector is not here anymore. And that means that you can really emulate complex pipelines with multiple outputs and some DisplayPorts, specific stuff like multi-stream transport and maybe HDR stuff. And that's all I wanted to show you. I wanted to show some pictures, but I don't have the time, sorry. So I hope this was good, and if you have any question about it, I think I have a few minutes, like 2 or 3 minutes to reply to them. Yes?
Thanks for the talk. Just want to make sure one thing, because I wasn't sure if I really got it. So the VKMS features you showed in the first demo, are those already upstream, or do you need to also manually catch that?
No, the only feature you have upstream is doing, where is it? Upstream you can do this pipeline or this pipeline. Yeah, on the mailing list currently you can do the first demonstration where you can create default stuff, so virtual connector, virtual encoder, and as many as you want. And all the work only on my GitHub is the rest.
Thanks.
Yes?
Since you mentioned you can allocate as many of these objects as you want via config.fs, can you run out of memory effectively? Because this was also one of the concerns for DTOs and config.fs.
Yes, you can run out of memory if you have not a lot of memory, because we need to keep for each device all the frame buffer you will ask to register. So yes, if you have a lot of them, you may run out of memory. And in DRAM, you also have some limitation about the number of stuff. For example, for one display controller, you can only have at most 31 connectors and 31 CRTC. I don't know anyone who wants so much output, but yes, you can.
That 31 comes from the
masking stuff, yes.
CRTCs which
Yes.
We probably have time.
Yes.
Can you show the last slide?
Which one? This one?
So maybe just a quick comment in reaction to the first question. If you're interested in VKMS and the work being done, I suggest that you participate on the mailing list because we've had some trouble getting the code reviewed and merged. So if more people who are interested can grab the batches, test them, report back, show that there's some interest, that would definitely help in getting more of that work, which has been a challenge for the past year.
Yeah.
Thank you.
Thank you.